As usual, welcome to the June meeting, Geology Club. On behalf of Andy Wyatt, and Jake is not here tonight, and myself. We all are just amazed and just overwhelmed that we have such a great club already. It's been such a short time. This is our fourth meeting. We have run so many field trips. We've done so much. We've had great presenters on our meetings. And once again, we have another great one tonight. Steve Lindberg is the man. He knows more about everything geology. If you've got a question, he can probably answer it. So we'll have him on here tonight. But first, I want to run through. So I do have a Dirtman report, and we've got a giveaway. So we'll get to that here in a second. But let's get to some club updates real quick. I want to make sure everyone's going to the right Facebook page. We've had some confusion, including myself. Turns out I wasn't even an admin of the correct page, so I was doing everything on the wrong page. So make sure you're going on Facebook to New Geology Club. You'll see this logo. You'll see this picture from our very first field trip, which June 21st, we're going back to National Limestone. It looks like already 70 people have shown up. So I want to redo this picture with only like 3-month difference to have a massive bunch of people. So that would be awesome. Upcoming field trips, like I just mentioned, the 21st, 9:15, there is a sign up for that. Just so we know how many to expect. I got to let them know about a week in advance, so I'll probably be calling on Monday, just to let them know and update them. Pisa Club is getting in this weekend. I've heard some rumors they did do a blast in Middleburg. Nothing so far from Mount Pleasant Mills. But we'll hopefully maybe in the next week we'll get one. We'll see. We'll see what happens. So after that, July 5th, the Brandywine Blue Quartz. That's one of these trips that are limited, but we'll run them again. We've done a few of these already this year that a limited quantity of people can go. We're going to rerun them, so no worries on any of them. You'll get your chance. And then another limited run, August 2nd, the C.K. Williams Quarry. Now this is radioactive, so keep that in mind. Doesn't bother me. You saw my last Dirtman report. I got like 15 x-rays one day in the back of a pickup truck. So I'm not too worried about it, but if you're sensitive to that kind of stuff, you probably should avoid that one. But that's gonna be great. I'm looking forward to it myself. I'm gonna go on that one because I've never been there. So upcoming events. So as former president of the Central PA Rock and Mineral Club, this is one thing that I am actually helping to lead. They are hosting the Rock Swap this year, which so I'm just trying this out there. I want everyone to come out. Geology Club is going to be a part of this, a big part of it. I'll be doing gold panning demonstrations. We're going to have talks on one of the iron furnaces. We're going to have talks on basically safety when cleaning with chemicals and stuff like that. And then Jake's going to do a tools presentation too. So all good stuff. We're going to have painting on the Susquehanna because right where that pavilion is, you can walk out. And last year during the Central PA picnic, I did a Dirtman report. I basically got one piece of gold in one gold pan. I went right out there, found it right away. So I can show you all, and it'll be a great day. Marietta Riverfront Park Pavilion. It's going to be awesome. So the 28th, completely free event. So bring all your rocks that you don't want and give them out to all the kids because they want them. So it's going to be great. This is new. No one's heard about this one yet, kind of. So I went and visited with the Indian Steps Museum. They wanted me to do a fluorescence presentation. So I was like, well, let's draw some people. Let's get some people here. And maybe let's do a social event. We've always talked about since the start of Geology Club doing social events. So let's go and meet up at July 19th at the Indian Steps Museum, York County. It is a beautiful, picturesque park. It's right on the water. You want to go fishing? It's right there. You just walk down across the grass there. They got a koi pond. They have a waterfall hike. It's like this little hike up through the Wissahickon schist that's there. It's beautiful. The surrounding rocks. But the museum itself is all rocks. It's all the native tools and all that stuff. So this is an amazing spot for us to just talk about rocks. They have a pavilion. So I'm going to be doing the fluorescence presentation. There's going to be crafts and all kinds of stuff put on by there. I'll have my trilobite crafts there. So if you want to come out and decorate a trilobite, I'll have them. But other than that, we'll just do a swap sell. This time sales are allowed. So if you want to bring some stuff, some flats to sell, I'm sure the general public will be coming to this one as well, because they're going to advertise this out across general local media and stuff like that as well. So great time for us to be us in a great setting and, share with the general public. So it's going to be a great time. July 19th. All right, let's move on to some of our, people that we like to shout out to. Jerry Jones, as always, he just did a Cadorus days smashing. He was giving hammers to kids and letting them smash rocks that he had brought down from Schuylkill County for fossils and stuff. That was a great thing. So I've helped with that in the past. Jerry Jones Zoom Rock Room. Just email jonesgeo@comcast.net and get on that list, and he sends you a free link every couple of weeks. It's the first and third Tuesday. That's why we have our Geology Club meeting on the second, because I never wanted to step on the rock room. I love the rock room, and I've been there since the beginning, so we'll continue to do that. All right, Geology 365. geologyclub.org comes from Ryan Klockner at Geology 365. He is the man. He has free online collection software for everyone, and also, the ability to manage a website, all that built in right into the software. He's a great guy, and he's always willing to help. So geology365.com, check it out. Jeannie Smith, she's in the room tonight. Jeannie, do you want to say anything about Herkimer Diamond Detective?
Oh my gosh, I got to click all my things on. Well, it's just that it's this little project that I started, and I actually did my first vending in my area, Rochester area, and just putting out information about the Herkimer community. I'm finding that a lot of people, even in Western New York, have never heard of it. So I'm sharing basics about Herkimer diamond mining and taking samples and showing people, and it's just fun to watch them be in awe, thinking that something like that exists in raw form. So yeah, I'm just kind of out there pushing or sharing, not pushing, because I let people come to me, because I'm not a pushy person about it, but because they're very attractive. Anyway, I'm out there just sharing the information about it, and it's been really fun.
All right. Well, thank you, Jeannie. She was going to be our August program. Now she's going to be our October program. So you will get to see all about that. But she'll be back.
Okay.
All right, and my page has stopped moving here. There we go. All right, Robert Beard, Bob Beard. I filmed one of them. I love him. He's a great guy. I've gone on field trips with him. He does the books, rock-hounding series. They're great. In fact, rock-hounding Pennsylvania and New Jersey. He just released his second edition. I highly recommend that one because I'm in it. So, all right. And before we get to Steve, I'm going to stop sharing. Okay, let's do the Dirtman Report real quick. So this is the last in the series of the North Carolina Dirtman Reports that I filmed down with Daniel Coleman. This one's been in the can for a while, and he's been itching for it to get released. Now I can finally do that after you all see it tonight, because I wanted you all to check it out first. This was supposed to be on the Rock Room, but we just had technical difficulties for a month. So this has literally been waiting a month for everyone to see. So I am proud to show it to you all tonight. And here we go. Everyone, please enjoy. Oh, wait a minute. I have to turn off. Give me 1 second. All right. Here we go, everybody.
Durban here with
Daniel Coleman.
and I am actually at a Digging with Daniel event. I am down in North Carolina and this is going to be great. Let's do it.
Let's do it. Let's rock.
Hell yeah. So I started right off, just threw a gold pan in the stream just to see. There's so much quartz here, so much mica. I figured, you know, what the heck. Let's just see what's in there real quick. And right away, first pan, I pulled out a point. That's a point right there. And then the whole backside is like celestial, like points going up the side of it. It's pretty cool. So I haven't even gotten to the bottom of the pan and I've already got a crystal. Okay, just got to the bottom of the pan. One pan, and I've got gold. So it's hard to see, but it's there. That's gold. Oh yeah, that's pretty cool. So all I really did for that gold was I just pulled a little bit out from underneath this big quartz boulder. I'm gonna do it again, see what the second pan gets me. I got crystals and gold in one pan. That's probably the best pan I've ever done, just because crystals too. So heck yeah, let's do it again. There we go. There's another one. All right, so pan number 3. Every single pan just has gold in it. Check this out. See that? There's actually 2 pieces right there, a big one and a small one. North Carolina, baby. So I kept on messing with the finds in that pan. There's more gold. There's probably 4 pieces of gold in here. Here's another one. Right there. Oh yeah.
Oh my God, look at that. Look at Bethany.
Wow.
Oh my goodness. She just pulled that out.
It's got some facets.
Bethany. And she's still digging. She's not giving up.
Now this is how you clear the brush when you're mining. You need a guy with a kilt, with a long broadsword. Well, it's not a broadsword. What's that, an officer's sword? Or what?
A hanger.
All right. What's your name, sir? All right. Now this is the way to do it. Love it. For those of you who don't know Daniel, his story is one of absolute humbleness and giving back to the community. A few years ago, he lost his son, and after that, going to the absolute lowest of lows, he went into the backyard and prayed to God, asking for help. Shortly after, he decided to mow the lawn. Right where he was praying, he hit and ran over with his lawnmower a large 1 foot, at least 1 foot large crystal plate. After that, he started finding crystals all over the place. He eventually became a manager at Hidden Night. After that, he started finding all these sites all over Catawba County and local counties down here, and started putting on Digging with Daniel events, getting the community engaged. I mean, the event today has kids all through it, and he was great with it. He has his own son now, and his life has changed, and he is doing good for the community. Something I completely celebrate. So, Daniel, you are the man. Great job, doing a great job for this community. He would have told his story, but he already had to tell it a few times today, so he let me tell it for him. So, great story, great place. Found the most gold today I've ever found, and I'm still going. Nice point here. Oh, yeah. It's small, but it's good. And there's another one. Getting a little tired there. Pans, a lot of strength. Never done this many pans in a row. There's lizards in North Carolina. What do you know? right. Daniel was like, "Yeah, check this crystal out. Check this out." Oh yeah. Wow. That's got some stuff on there. Look at that. Very cool.
Super
Yeah, that's a specimen right there.
specimen. That came from my buddy Paul,
Right where he was just digging.
right where he was just digging. It was an awesome pull. At that little area, I pulled a couple of these just like it, but I'm super proud that he's found one. So
Yeah,
yeah,
that's
good
right
job.
where that's right where they were clearing with the sword, using the sword. So
So that came from that location.
Very
That's
cool.
awesome.
yeah, sword use required.
Sword use required. Yes. Yes.
Oh, yeah.
But we had a great day here with Andrew and Corey, Rockhound. It was great to have them all the way from Pennsylvania. And I know digging with Daniel is a great journey. I help the people along the way, and if they need me, I'll be there for them.
He's one of the nicest, best, knowledgeable people that I've met down here. It's absolutely amazing to
You've
meet
been a
him.
great soul to have this weekend. You really had. You brought me out of the house.
Awesome. It's been a great weekend.
Great
environment.
weekend. Great environment. Great people. Kids. You know, rocks. Great rocks.
Oh,
You
yeah.
know, and that's what it's all about.
And gold.
And
we got gold.
That is the kicker. We don't only have crystals, we have gold.
Thank you, sir.
Thank you,
Appreciate
bud.
it.
Hell yeah.
Zerman here, bringing the geology to you in North Carolina this time. See you next time.
Next time.
All right, everybody. I hope you enjoyed that. That was probably my best gold day ever. I have a gold dredge. I've been mining gold for years. Maine, Virginia, North Carolina, Pennsylvania, everywhere. That was the best day ever. It just was every single pan. I wasn't even using a dredge. It's just every single pan had gold in it. I was just, it was heaven. So anyway. Let me get on to I hope you all enjoyed that. I'm gonna drop it on Facebook tomorrow. So this is the giveaway, including Jeannie just said that she was going to add a Herkimer Diamond Detective Kit. So we'll figure out how to get that to you, which is awesome. Thank you, Jeannie. I have
Yeah.
one myself. It's just up at the house right now, so I don't have it to show off, but thank you, Jeannie. That's really, really cool. Do you have one? There you go.
Yeah, I'll just mail it. You send me the name and address and I'll send it out.
All right, cool. Yeah, it's a box full of awesome. So, and then you'll get a second box full of awesome from me. So what we have here, this is New Ringgold. So last Sunday, I led a trip for Central PA Rock and Mineral Club to New Ringgold. Dean Rocco happened to be there from last month's presentation. He was digging fossils, and we were both finding diplorofossils, which was awesome. Found some of the largest pieces of diplora I've ever found. But he also found a small, you can't see through the bag, but it's a small tail of the Pennsylvania state fossil, the Eldredgeops rana. I threw in a head, and then there's also a gastropod in there. So that's New Ringgold. Also, from our field trip with Steve Lindberg tonight, I have specimens that I personally collected out at the New Paris Quarry. So there's fossils, and there's a little sliver of calcite in there with some fluorite in it. So two news, New Paris and New Ringgold. That's our giveaway tonight. So if you want in on it, it's completely free. All you have to do is put a number between 1 and 100 into the chat while Steve is doing his thing. And after Steve's presentation, we're going to draw a number. Whoever's closest without going over is going to be the winner. And I will ship this to you free. So will Jeannie. And that is awesome. And because that's what we're here about. This is just sharing the love of rocks. So go ahead, everyone. You got a little bit of time, but yeah, go ahead and get that on in. So tonight we have an introduction to structural geology. This is something I love. I love finding little pieces of structural geology that has folds and all kinds of stuff in it that are hand sized. It's kind of like one of those little niche things that you get as a rockhound. But when it translates to massive sides of hills and mountains and road cuts and stuff, it's really cool. So, no other person I could think to have here to talk about this other than Steve Lindberg. I call him Professor. He tells me he's actually not, but he's the professor. He knows more about everything. And he is also the president of the National Association of Geoscience Teachers, Eastern Section. You all may recognize that because they awarded me the Digman Award this year. Well, he beat me. He got two for his achievements in the National Association of Geoscience Teachers Association. So without further ado, Professor Steve Lindberg, it's all yours, sir.
Let me share the screen. And can everyone, am I unmuted?
Yeah, we got you. We got
Oh,
you.
okay.
Yes.
Brett, and you can see the screen?
Yep, everything is
All right, so we're good. Well, Andrew, thank you. And Geology Club, thank you so much for the invitation to speak to you tonight. This was actually the topic for tonight, an introduction to structural geology. This was a special request by Andrew. He said he was really into structural geology, and I said, well, we can do something like that in an upcoming presentation. And I have changed this about 15 times over the last month and a half. So if those of you that don't know me, I'm Steve Lindberg. I'm an adjunct professor of geoscience at the University of Pittsburgh at Johnstown in the Department of Geosciences and the Environment. I've been there since 1997, and I've pretty much taught courses from geological field methods to introduction to paleontology, meteorology, introduction to astronomy, physical geology, earthquakes and volcanoes, and kind of runs the cycle as we need to meet the needs of our students. So welcome to the program tonight. Just a couple of notes. I've tried to put into Andrew, do I have like an hour, 45 minutes? I've tried to put into like an hour presentation or less what would normally be an entire semester of structural geology. Hopefully I cover most of the things that you'll find interesting, but there's some things that I do not cover because it's simply like was beyond the scope of what we could really do realistically in one evening. And that is, I really don't get into micro structure, the fabric, the microscopic fabric that we see in igneous sedimentary metamorphic rocks due to deformation. So there's no metamorphics and really no igneous included in this presentation. I kind of focused on the big general topics of what a structural geologist does and how we map structure in the field and how that translates into what we see on the surface of the earth. So, I hope that's the second one. All right, so any university, any college that offers a degree in geology or geoscience usually includes a course on structural geology. Sometimes they have structural geology part 1, structural geology part 2, but it's an integral part of any type of geological geoscience degree. So structural geology is the branch of geology that deals with the deformation of rocks on both the large scale, the medium scale, and the microscopic scale. When rocks are exposed to forces within the crust of the earth, they can snap, they can bend, they can recrystallize and become new rocks. And structural geology is the specific branch of geology that deals with understanding what happens to rocks when they are exposed to forces, to stresses within the crust of the earth. Structural geology is an important part of geology, especially engineering geology and civil engineering, because structural geologists are usually the consultants for all mining operations. You need to know what the rock layers are doing below the surface because before you can begin mining, the construction of large buildings, skyscrapers, what does the bedrock look like? Is it faulted? Is it brecciated? Is there a chance of slides? When we build tunnels, we need to know what we're encountering. Some of you may know, just a side story, the Paw Paw Tunnel on the C&O Canal when they were constructing that tunnel. I don't have that in here specifically, but the rock layers were tilted at a very high angle. And as the workers were constructing that tunnel, the rock layers would break loose and slide down into the path of the tunnel, killing the workers. And we'll kind of look at why that happens this evening. So there was a structural geology problem. Pipelines, especially dams, pipelines, dams, utility lines, tunnels, bridges, all have to take into account the aspect of structural geology. What's happening to the rocks below the surface of the earth? Structural geology is also very important in oil and gas, petroleum exploration. I don't really specifically cover that tonight, as that's an entirely different field, but just kind of a little preview of what could be a future program is over on the bottom left. A structural petroleum geologist would look for things such as what you see on the lower left-hand side. This is a fault-bounded petroleum and gas trap, where because of the fault and the shifting of the rocks, the oil and gas has been able to migrate up through a porous rock, and then it's stopped. It's trapped by a non-porous shale, and that produces a reservoir. And that's one specific type of deposit that a petroleum geologist mapping the structure would look for. So, the other views that you see on the screen there, roads will fail, rock falls will take place, and that's all based on what's happened to the rocks in structural geology. And here are some structural geology problems. These are examples of rock falls and slope failure due to planes of weakness. I'm sure you're all accustomed to seeing things like this. This is the type of problem that a structural geologist would advise road construction crews on how to remediate something like this. The view on the left, you can see the highway at the bottom, and on the side of the highway, that road cut, those are sedimentary rock layers, and they are tilted. They are tilted or dipping at a relatively high angle. And these are the bedding planes between the rock layers. And those individual bedding planes between like a sandstone and a shale provide a plane of weakness and a place where those rocks could fail. And what will happen is if you intersect tilted beds, there's a chance for those beds to break loose and slide down, causing a rock slide. And you can see the evidence of that in the picture on the left-hand side. On the right-hand side, these are horizontal sedimentary beds, but they are highly fractured with vertical cracks that we call joints. And we'll talk about joints later tonight in the program. Those of you that have been to the New Paris Limestone Quarry, you've seen excellent examples of jointed sedimentary rock that's prone to failure. So the layers of rock that you see here are a limestone. Because of the stresses placed on the rock during tectonic activity, the rocks have been fractured in the vertical in two different intersecting sets. That provides a plane of weakness where the rocks can break loose and tumble down. Not the same as a slide that you see on the left. All structural geology. Here's a recent slide, rock slide that took place down in one of the southern states. These are red shales and sandstones. And the road crew that you see there is facing the same problem, where the road cut through a hill and the rock layers were tilted or dipping in the direction coming down towards the road. So when they cut through that hill, they automatically produce a natural zone of weakness where those rocks can break loose and slide. And the two little cartoon diagrams that I show over on the right-hand side are match what you see in the photograph almost perfectly. We have tilted, inclined, dipping layers of rock, and the bedding planes between those rocks are planes of weakness, and they're bound to produce a slope failure. And one of the things I want you to notice is look at how perfectly smooth that surface is. That is a bedding plane surface. that has not been planed off by a tractor or an excavator. That's exactly what it looked like after these rocks tumbled down, and I imagine they've already been pushed back from the highway. So another example of how structural geology comes into play. So let's go back to the 1700s, and one of my favorite historical geologists to talk about, and I cover this quite a bit in my prehistoric life class, Scottish geologist James Hutton is often considered by many people, many geologists, to be the father of modern geology and the father of structural geology. And Hutton mapped much of Great Britain and Scotland. And one of the most famous places that Hutton visited is on the North Sea coast of Scotland. And he visited this in 1788. And his sketches, which were carried on by other geologists, contemporaries of his, but Hutton was the first one to go to this very, very famous outcrop called Sicker Point. And what Hutton observed was one of the first structural geology rock outcrops to be described, or at least an attempt to describe what had happened here. And what Hutton observed, and of course on the right-hand side, this is a modern photograph, but what Hutton observed was rock layers at the bottom that were tilted and inclined at a high angle. And then there was an irregular contact where it looked like those tilted rock layers had been worn away and planed off by some unknown force. And then on top of these tilted rock layers were totally different rocks of a different age with different fossils that were at a different angle. And Hutton called this his great unconformity. Unconformity meaning that this irregular line separates two distinctive types of rocks in totally different attitudes. And there's a little sketch that was made by Charles Lyell, another geologist, English geologist, that was attempting to describe what happened here. When James Hutton saw this, he realized that something like this could not happen in 10 years or 20 years or 100 years or 1,000 years. And this led him to believe that the Earth was extremely old. He wasn't exactly sure how old the Earth was, but he realized that the Earth was extremely old. And in order for rocks to be deposited like this and then worn away and then redeposited, must take enormous forces within the Earth that are bending and twisting those rocks and then going back under the ocean, the sea, to have new sediments deposited on top. To structural geologists, this is one of the places that I'm going to say not just a structural geologist, but every geologist, going to Sicker Point is kind of like an epiphany. It's on the bucket list of places that every geologist wants to visit. And in March of 2018, Pitt Johnstown, we took our students there. March does not present the best weather in Scotland to go out and sightsee, but we managed. So here we are. This is on the North Sea, wind blown. The day that we were there was almost gale force winds. There was a heavy driving rain, but this is the north coast of Scotland. These are our students, and I was all battened down with waterproof clothing. And I don't know if you can tell, but if you look at these spectacular cliffs in the back here, you can just make out there is a huge downward warp in the rocks right there. And that is an enormous syncline that's been eroded away and exposed along the coast. So these are sedimentary rock layers that date back about 400 million years. And you can trace these rock layers as they bend down and then come back up. And you can see the sloping rock layers here. Well, Sicker Point is not easily accessible. If you ever go to Scotland and you want to go to Sicker Point, you work your way to the Scottish coast. And there's kind of small little signs and cow paths that lead you to these extremely high cliffs. You have to scale down a very steep hill. That is a barbed wire fence, and they have rope attached to it so you can lower yourself down. And that outcrop of rocks with the large 20 and 15-foot waves crashing against it on this day was Sicker Point. And we managed to get down to the point, and there it is. There's a rock hammer there for scale. These are the tilted older rock layers down below, and then the unconformity, and you can see a second set of tilted rock layers above it. And then we have some of our professors and students sitting on that outcrop. So this was really the beginning of structural geology, and Hutton kind of laid the groundwork for the study of how rocks fracture and bend and break within the crust of the earth. So let's cover a couple of principles first, and we'll go back a few hundred years or 100 years before James Hutton, and we'll talk about there was a Danish physician and geological pioneer by the name of Nicholas Steno. And Steno was very keen at observations. And Steno studied geology, and he came up with a set of 3 principles about geology that we still hold true today. These were correct back in the 1600s, and they're still correct today. Hutton observed that when rocks form on the earth, they tend to form in horizontal layers. And we have a picture there. That's a photograph from out west. I don't know who that young person is, but this is a nice example of showing Hutton's first principle. It is called original horizontality. Rocks that are deposited, either sedimentary, igneous, and sometimes metamorphic rocks, tend to form in horizontal layers. And the horizontal layers tell us that they're undeformed. They have not been affected by the forces of stress that act in the crust of the earth. They have not been tectonically deformed. So to a geologist, the principle of original horizontality is extremely important. Rocks form in horizontal layers, and they remain horizontal unless forces act on them. The second of Steno's principles was the principle of superposition. And superposition tells us that when you look at a stack of horizontal rock layers, the oldest layers are at the bottom and they formed first, and the youngest layers are at the top. And you're looking at a sequence that took place through geologic time. And if, for instance, if you were digging for fossils in that sequence of rocks that that person's standing in front of, you would find the oldest rocks down here at the bottom, and the oldest, most primitive fossils. And then as you proceed up the stack, you would find the youngest rocks and the more recent fossils at the top of the pile. And that is the principle of superposition. The only time the principle of superposition does not hold true is if the rocks have been acted upon by some type of force. They could be flipped vertically and then overturned upside down, and that becomes a problem in geology. And there are ways that a geologist can figure out. It's easy for us to tell if rocks have been flipped upside down. One of the ways is we see a reversal of the order of sediments from large to small that form in a sedimentary rock layer, and sometimes the fossils are inverted, worm burrows and things like that. Steno had a third principle called the principle of lateral continuity. And I don't show that here, but what lateral continuity tells us is that a rock layer is planar and they can extend for hundreds of miles in every direction through the crust of the earth. Like here in western Pennsylvania, we have the Conemaugh group of rocks and the Allegheny group of rocks, which are carboniferous in age, and they extend across 5, 6, 7, 8 counties, all the way from Johnstown into Pennsylvania and up to the New York state line, down into Maryland and West Virginia. So those rock layers are continuous, even though you don't always see them. And eventually, rock layers pinch out or blend into a different rock, and they change composition or character, and we call that a facies change, Facies. Another important relationship that comes into play with structural geology is the principle of cross-cutting relationships. This wasn't Steno. This was Charles Lyell in his 1830 book, The Principles of Geology. Charles Lyell stated that the principle of cross-cutting tells us that when you look at rock layers, and it doesn't matter if the rock layers are sedimentary, igneous, or metamorphic, when you look at those rock layers, if they are cut by something, if something slices through those rock layers, the thing that slices through them must be younger than the rock layers themselves. And there are spectacular examples of this all across the earth. This is at the bottom of the Grand Canyon. These are rafters on the Colorado River. These are extremely ancient red beds, sedimentary layers of sandstone and shale. And then at some time in the distant geologic past, hot magma from within the crust of the earth melted its way up through these rock layers. And we call this an igneous intrusion. And the specific term for this is an igneous dike. And this was hot magma that melted up through the rock layers. Doesn't always make it up to the surface. Sometimes it solidifies, but cross-cutting relationships tell us that this intrusion must have come after these rock layers formed. And there are places on the earth where we have 5, 6, 7, 8, 9, 10 intrusions that cut all across each other, and we just need to look at them and we can figure out the order in which they formed. The photograph here on the right, these are sedimentary rock layers that are broken by a fault, an earthquake fault, and you can see that the rock layers have shifted and they no longer match up. We know that the earth moved, the fault took place after those rock layers formed and were lithified into solid rock. So it shifted the rock layers. Here's a spectacular example of sedimentary layers, limestones and shales, that have been cut and intruded by a dark magma, a basaltic igneous dike in the geologic past. So we know that these layers formed first, and then this hot magma melted up through the rock. It actually came vertical, then it went horizontal, then it went vertical again. A vertical or near vertical intrusion of hot magma is called a dike. So this part is a dike, and that is a dike. And a horizontal intrusion that squeezes between the layers is called a sill. So we can have both dikes and sills. And this is all part of figuring out the structural geology. So one of the things that we also need to talk about is an unconformity. And this goes back to what Hutton was describing at Sicker Point. An unconformity is fairly common in the rock record. This can be between sedimentary, it can be between igneous, it can be between metamorphic rocks. But an unconformity is a break. It is a gap in the geologic record where we are missing rock. We may not be sure of how many feet, 100 feet, 1,000 feet, 5,000 feet. We're probably never really 100% positive of how many feet of rock we're missing, but we know that there is a gap in the geological record. And sometimes the gap is quite large. Those of you familiar with the geological timescale, you can jump from Cambrian up to Cretaceous period and have a gap of 450 million years of history that is just gone. And what that indicates is that as the rocks were forming, forces within the crust uplifted these rocks. They were exposed to the atmosphere and weathering and erosion, and they were removed and planed away, and they've disappeared. Then it went back underwater. The oceans rose, or part of the continent subsided, and new layers were deposited on top. So there's basically 3 types of unconformities. The first type of unconformity is called a disconformity. And even after teaching geology for almost 50 years, I still get disconformity and nonconformity confused. And I have these little diagrams in my notebook, and I still refer to them when I'm out in the field. So a disconformity is an irregular break that represents erosion between sedimentary layers. So we had sedimentary rock layers forming, then there was a long period of erosion that wore away a rock layer, and then it went back underwater. And we'll see this as an irregular surface. Then we have an angular unconformity. An angular unconformity is Hutton's Sicker Point. We have the formation of rock layers. Those rock layers then undergo some type of deformation where they're tilted. The tilted rock layers are exposed to erosion. We sometimes find loose cobbles and boulders, pieces of those rock layers that are included in the next layers that form above it, which are horizontal. And that's an angular unconformity. And then a nonconformity is two different types of rocks that touch. You can have sedimentary rocks that are then intruded by hot magma. The hot magma solidifies, forming a dike or a sill or a larger intrusion, and that boundary between two different types of rocks is a nonconformity. It can be igneous and metamorphic. It can be metamorphic and sedimentary. And these come into play in structural geology too. So I've just repeated the diagram here, and I've just given a little more of an explanation about how each one forms down below. And we see these when we're out working in the field and attempting to map rock layers. So a geologic map is the primary tool of any geologist, but especially a structural geologist. And I just want to move my little, I can see all of you in a little sidebar here, and that sometimes gets in the way. So if you've ever used a topographic map or any type of map at all, a map shows the features on the surface of the earth. A geologic map simply shows the rocks that are visible on the surface. And I like to tell my students, if you could clear away all the trees and all the leaves and all the topsoil and expose the nice, bare, naked rocks that are on the surface of the earth, that is what a geologic map shows. We show, it's nice to have a geologic map in color. It has the different rocks showing up in different colors. The geologic map that you see here is of the Gray Fossil Site in Tennessee. The little squiggly lines that you see in the background, this is on a topographic map, so we also have the contours on here. But a geologic map uses different colors to show the different types of rock and the different rock formations, the shales from the sandstones, from the conglomerates, from the limestones, from the igneous rocks. We can also show faults, places where the rocks have been broken and moved. We show contacts where one rock ends and the next one begins, and those are shown by the heavy black lines on here. The little symbols like OC and OK and OLB, these are the abbreviations for the names of the rocks that appear in this region. And this is what's known as the stratigraphic column. When we make a geologic map, we list the rocks in order of age in the stratigraphic column. The oldest rock is always put at the bottom. Sometimes there's a little bit more detail here. It will actually give you the age in years or more of a description, but C stands for Cambrian period. So these are about 500 million years old. O is Ordovician, T is Tertiary. So the little abbreviations are the names or the abbreviations for the rocks, and we give a little bit of a description. There's a scale of miles and kilometers. And then we've got all these other little symbols on here that we'll talk about. These little T-like symbols that are known as strike and dip symbols with numbers next to them, and arrows with other arrows pointing in different directions. And we'll talk about all that tonight. Not only does a geologic map show the rock layers, but it also can show stream gravel, deposits from streams, which we call alluvium, and rock slide material, piles of rocks like a rock slide that comes down off a mountain, and we call that colluvium. So if you've ever used MacroStrat, the web-based, this is what RockD is based on, the iPhone, the Apple version of a geologic map. If you've ever used RockD, the web-based version of RockD is MacroStrat. I tend to use MacroStrat more than I use RockD, but here's the head title for the webpage for MacroStrat. And those of you that have been to New Paris Quarry, here it is. So here is the Altoona would be to the north here, and I've zoomed in, but the closest town to New Paris is Schellsburg, and this is the Chestnut Ridge anticline, which we'll talk about a little bit later, anticlines, and the New Paris Quarry is that last little light colored dot that you see right there. The pattern of lines that you see on this map is telling us what the structure is of the rock layers exposed on the surface and below the surface. So the little yellow lines on here are the boundaries between the rock layers. All of these layers are named. This is the Allegheny Front, and this is the plateau, where the rock layers are basically horizontal, and this is the ridge and valley, where the rock layers are folded. I didn't include the rock names on this. The little black lines that you see on here are earthquake faults. And you can see that along some of these faults, the rock layers have been displaced. None of these are active today, but they were in the past. So geologic maps, we've been making geologic maps as far back as the 16 and 1700s, and I just wanted to show you this one. This is from, you can actually still find this in bookstores or online. There is an atlas of geologic maps for every county in Pennsylvania that was mapped back in the 1800s. This is my county, Cambria County, and this is from 1884, the geologic map of Cambria County, and it shows the different rock layers in stratigraphic order and their ages, and there's a little bit of a description there. Here's the geologic map for Pennsylvania. If you were at New Paris a few weeks ago, these copies of this map are available through the State Geological Survey, and you can call the librarian and she will mail you a tube of 10 or 15 of these maps. I know I had a bunch of them at New Paris. Every color on this map is a different rock formation. The key is at the bottom, and it describes the rock and gives you the age. And there's a lot of structure here in Pennsylvania. I often tell students that Pennsylvania is the structural geology paradise. I zoomed into that map, and here's where I'm located right now. I'm in Johnstown, and so here's the zoom up of that map. This is Johnstown. This is Laurel Ridge, which is an anticlinal structure, and this is Conemaugh Gorge going through Laurel Ridge, and the Conemaugh River flows through Laurel Ridge. It's an upwarping of rock that looks like this. It's an upward shaped bend of rock, and the Conemaugh River has worn its way down through Laurel Ridge and has exposed much, much older rock all the way back to the Devonian period. So a cross section through New Jersey, a cross section through Pennsylvania. We'll talk about how cross sections are made. I thought you would be interested in seeing this. These are generalized cross sections through Pennsylvania, beginning in the west. So picture Pittsburgh way over here on the left-hand side, and then coming across the state on the turnpike, and Altoona and Bedford would be right about here. And then this would be about where Harrisburg is in what we call the Great Valley. If you've ever traveled the turnpike, Kittatinny Mountain and Blue Mountain, the tunnels go through these ridges, which are the result of enormous folds in the rock structure. Harrisburg would be right about here. This is South Mountain, which is the northern extension of the Blue Ridge. Gettysburg would be in here in the Triassic lowlands, which is a graben, a downward faulted valley, and this would be the Piedmont, and coming down coming into Philadelphia and the coastal plain. And then there's another simplified example of the cross section. So how does a structural geologist make a cross section? A cross section is a view through a slice of the earth across a geological map. In order to make a cross section, we usually make the geological map first. So what you're looking at here on top is the geologists that map this area, and I think this is just a made-up map, but the geologists that made this map traversed back and forth across the map and made detailed sketches of the rocks that they were walking on or the samples that they were picking up. They noted the attitude whether the rocks were horizontal or tilted or dipping, and the direction they were tilted in and how thick they were. And after they constructed the geologic map, they use that information and they draw a line across the map. And that is what the cross section down below here, I want to move my little panel here to the side. Let me see, I think I just lost everyone. There we go. So a cross section, picture taking an enormous knife and slicing the crust of the earth and opening it up. It's like slicing a birthday cake in half. So you have this round cake that's whole, and you slice the cake in half and separate it, and you're looking at what the rock layers are doing below the ground. Part of the work of a structural geologist is to take the information that we have on the surface of the earth and extend that to what it looks like below ground. And this is extremely important in civil engineering and mining engineering, figuring out what the structures are like, where the weaker rock layers are, the more durable rock layers, is there infiltration by groundwater. So that is how we construct a cross section. That we can also reconstruct. You can see the dashed lines down here. We can reconstruct where rocks are missing and what they might have looked like in the distant past before erosion. So geologic maps and cross sections and structural geology can get quite complex. This is a map of the Moorfield Quadrangle in Hardy County, West Virginia. And what you're seeing on the left-hand side here, every different color is a different rock formation. And the full-size map is much, much more readable, but it has the abbreviations and the names of the rocks. And there's more information that appears on here. The little red lines have arrows on them, and they're indicating the direction that the rocks are tilting in. And you can see how close these red lines are. So what that's telling us is that if you walked across this area, the rocks are folded. They're tilted up and down in a very tight pattern. And I've actually given this map to my students. I give them that map and a piece of graph paper, and the line is drawn across it. And I give them about 10 or 15 minutes. And I say, okay, come up with the best. What does the cross section look like from A to A prime? And there it is. So that's what the cross section looks like across that line. That's some pretty complex structural geology. I don't expect them to do that in 15 or 20 minutes, but I at least expect them to be able to figure out the major structures, the synclines and the anticlines, and we'll talk about those in upcoming slides. So geologic maps and structural geologists use a variety of symbols on the map to tell us what is happening to those rock layers. And this is not all of the symbols that we use. It can get quite complex. There's a list of at least 100 different symbols, but these are the most common ones. The one that is probably used most often is called a strike and dip symbol. And for all of the complexity of structural geology, I have found over the years that students of geology have the most difficult time with visualizing strike and dip. Once they get the grasp of the concept of strike and dip, then all of these other symbols and all of these other structural formations kind of fall right in line. And we'll talk about strike and dip. So let's start with the basics. If you're making a geologic map of an area, the easiest region to map in is a place where the rocks are horizontal. There's very little structure there. We go out west and there's a lot of places, and even here on the east, where the rocks are horizontal. And if you're making a geologic map of horizontal rocks, you're pretty much looking at this. If my little board here, my piece of broken pine board, represents a rock layer, if the rock layers are horizontal and you're walking across the surface of the earth, you stay on the same rock layer until you start to go downhill and encounter other rock layers. And then usually if there's another hill, you'll pick up that other rock layer. On a geologic map, if the geologist wants to tell you, because if you're looking at a geologic map that doesn't have a cross section, how do you know the rock layers are horizontal? Well, on the map, the geologist will use that symbol. And what they'll simply do is on the geologic map, they will put a round circle with a cross in the middle. And when you see that on a geologic map, that tells you that the rock layers under your feet are horizontal. So on any geologic map, that symbol represents a horizontal bed. All right, what if the beds are vertical? And this is quite common here in Pennsylvania and other places. Rock layers can be smashed and folded and compressed. And that is a pretty spectacular road cut right there. Those rock layers are not horizontal. They have been tilted vertically. So how do we tell someone, if you're using a geologic map, that the rock layers are vertical? On the map, we use a symbol that looks like a cross with a long axis and a short axis, and that would be placed on the surface of the geologic map, and that indicates that that rock layer is vertical. So when you look at a geological map and you see this symbol, it's easy to visualize on a block diagram. So you're walking across the ground and you see this rock layer and you're able to measure it and you know that it's vertical. That's what your map looks like, and that's the cross-sectional view. You have vertical rock layers. So now we get to strike and dip. So here's the definition of strike and dip. Rarely do we have rock layers that are perfectly horizontal, especially in areas that have been subjected to deformation or plate tectonics. And Pennsylvania is the perfect example of that. Usually rock layers are tilted, and they can be tilted in many different directions. They can be tilted to the east, they can be tilted to the west, they can be tilted to the north and to the south. They can be rotated, all right? They can be vertical. Rock layers can be overturned. So on a geological map, how do we tell people that the rock layers that you're walking across are tilted? Now, sometimes the rock layers stick out above the surface, and you can actually walk up to the rock layer and see that it's tilted. And those of you that have been to the New Paris Quarry, you can walk across the tilted rock layers. But suppose the surface of the earth is completely flat, or they're only sticking up a little bit, or there's just a person using a geological map. How do we know that the rock layers are tilted? Well, we use a series of strike and dip symbols. The strike is the long line, and the dip is a shorter line. The short line points in the direction that the rock layers are tilted in. And when you're using a geologic map, north is always at the top, south is at the bottom, east is on the right, and west is on the left. So all of these rock layers are tilting towards the west at a 30-degree angle. That's pretty consistent. The rock layers change from limestone to sandstone to shale. That was part of the job of the geologist to map that out. This is a pretty big area. That's 1 kilometer. So this is a few miles across. So we have layers of limestone, sandstone, and shale that are tilted to the west at 30 degrees. The strike is the direction that the rock layers trend in when they contact the horizontal plane. And that'll be easier to visualize when I show you the next slide. But one of the things you can kind of visualize here is notice how the long line that we call the strike line lines up with the boundary between the rock layers. So although the boundary between the rock layers is a little uneven, and that's not necessarily an unconformity, that's just irregularities in the surface of the earth. Notice how the long strike line roughly lines up with the contacts between the rock layers. And what that's telling us is these rock layers are lined up in a north to south orientation, but dipping to the west at 30 degrees. So based on that, here's what the cross section looks like from A to B. Without even drilling or having a road cut to look at, you can look at the geological map, drop down the contacts between the rock layers, and then dip those rock layers to the west at about 30 degrees. The dip is the angle that the rock layers are tilted in relative to the horizontal plane. The strike is the intersection of the horizontal plane and the bedding plane, the dip. So here's another way to visualize that. I kind of like the black and white drawing on the right-hand side. You're walking through a field and you see these rock layers sticking up out of the ground. And if they weren't dumped there by a construction project, let's say they're natural, they're just big tilted rock layers coming up out of the ground, the angle at which the rock layers are tilted is known as the dip. And the intersection of a horizontal line and the bedding plane, the surface of the rock, and think of it as the direction the rock layers point in, that is called a strike. So if rock layers are horizontal, they have no dip and they have no strike. But that's fairly rare, especially here in Pennsylvania. Most of the rocks we have here in Pennsylvania have a strike and they have a dip, and that dip sometimes can be very low and the strike can only be a few degrees from north or south. But strike is the direction the rock layers point in. Think of that as a way to describe strike. It's one of the fundamental measurements that a geologist makes. And here's our young student geoscientist. He is using an instrument called a Brunton Transit, a pocket compass that is specially designed to measure the strike and dip and other features of rocks. Brunton was a company in Colorado, a famous company that first manufactured geological, we call it a transit or a pocket transit. This is kind of old school geology. I still have I have it sitting right here on the desk in front of me. I'll show it to you in a few minutes. I still have my Brunton Transit from the 1970s, which is actually a model that was made back in the 1930s. I have a fairly old one. It's kind of a classic Brunton that I still use. I had it at New Paris a few weeks ago and I was doing some measurements. But what that student is doing is there is a tilted rock layer coming up out of the surface of the earth, and he is using his Brunton Transit to measure the strike direction, which is notated a certain format, and then he's measuring the angle of dip. Not only the angle of dip, but the direction that the rock is tilted in. And then he's going to plot it on a map, and what he's measuring on the surface of that tilted rock layer translates into what you see here. So wherever he locates this on his map, that is the symbol that he's going to draw. He's going to use a protractor. He's going to draw in a long line on the map that is pointed 20 degrees east of true north. So there's true north, and that rock layer is pointing 20 degrees east of true north, and it's dipping to the southeast at 30 degrees. So hopefully I haven't lost you yet, but this is one of some people get this right away. I've had students that through all 4 years when they're graduating as seniors, they still have a difficult time visualizing strike and dip. And I found out that people that have very good like spatial, when you can visualize things three-dimensionally, spatially, you have an easier time with strike and dip. So, I think that skipped a slide. No, it didn't. So here is, this is my Brunton compass. This was actually, those of you that were at New Paris, I was using my Brunton, and here it is, right here. I've had this for as long as I've been studying geology. This is an original Brunton, and there's a mirror on it that's not used for checking your hair. to make sure it's nice and neat. The mirror is used for sighting on different objects and taking back bearings. There is a magnetic needle in the Brunton and 2 leveling bubbles. And that is a photograph of me holding my Brunton at New Paris. And I was actually measuring a series of fractures on the sedimentary bedding plane. And I laid the Brunton down on the ground on this fracture. And I'll tell you right now, never do that. So that's a no-no, because you walk away and you forget it or someone steps on it. So you never lay your Brunton on the ground. Everything is done handheld. This is a quad Brunton. It's marked in 4 quadrants: 0 to 90, 0 to 90, 0 to 90, 0 to 90. The interesting thing about a Brunton compass is the east and west directions on it are backwards. So right now I'm pointing, that's the sighting arm, I'm pointing the compass north. So if you face north, west is on your left and east is on your right. But if you look at the compass, west is marked on the right-hand side of the compass, and there's the E for east. And people look at the compass and they say, what's going on? You got the compass directions are backwards on the compass. How can west be on the right-hand side? And that is because the magnetic needle, when you turn the compass and point the sighting arm in a certain direction, it's a true read compass. You don't have to invert the directions. So I think you can see this. There's 0 right there. And the white end of my needle is pointing at about 8 degrees to the east. So what that means is my sighting arm of the Brunton, I was looking 8 degrees east of north. And what that means is the strike of these fractures on the ground, the way I would write that on a geologic map would be north 8 east. And that's what I've written up here. So on my geologic map, I would put that strike and dip symbol. I would put the long line tilted 8 degrees to the east with a short line and an 8 next to it that indicates the dip. So there are 2 types of Bruntons that you can get. The first type of Brunton is a quad Brunton. It is marked in 4 quadrants from 0 to 90 degrees, and that's what I use. And some geologists like to use an azimuth Brunton. You can get a Brunton that's marked from 0 to 360, which is from true north all the way around and back to 0 again. West would be 270 degrees, east would be 90, south would be 180. Some geologists prefer an azimuth compass. They write everything down in terms of 0 to 360. Others write things down in terms of northeast or northwest. I prefer the northeast to northwest method. So here's how we use a Brunton. This is a geologic map. It's just this is actually part of over by New Paris. I just zoomed in on it. So here's the yellow rock layer. North is at the very top. You stand on this rock layer and you aim your Brunton in the direction the rocks are going in. And the Brunton told me the needle pointed to 15 degrees east of north. So that's the strike line. Notice the strike line kind of roughly parallels the borders of the rock layer. Once again, this is not the cross section, this is the map view. So if I were mapping this area on my geologic map, I wouldn't put the white square there. I just highlighted it in white so it would show up better. But if I were making this geologic map, I would draw that line and then I would put the dip line. The dip here is 32 degrees to the southeast. So my Brunton is pointing north 15 degrees east. You can also take a back bearing. It's the opposite direction, and that's easier to see when you plot it on a quadrant diagram. So my magnetic needle on the Brunton would be pointing in that direction. It would be pointing 15 degrees to the northeast. The dip is 32 degrees to the southeast. And the back bearing is looking in the opposite direction, and that would be south 15 degrees west. In quad mapping structural geology, we tend to, we really don't use the southern half of the compass. Everything is either northeast or northwest. It's kind of a difficult habit to break, but it makes it a little bit easier. So in structural geology, if you're using a quad compass, we normally just designate everything either northeast or northwest. And if someone asks, we can figure out what the back bearing to the south would be. So here's another example. Here's a geologic map with a whole bunch of rock layers, a fault, and an intrusion. I put the strike and dip symbol on this brown layer down here, and that's what that symbol, that's the strike. So we only read the northern quadrant. We would never say south 40 degrees east. This would be north. This is actually north. 50 degrees west is the direction that line is pointing in. And the dip is to the northeast at 40 degrees. So on a quadrant, that's what that line would look like. So there's my strike line and there's my dip line. So the red lines that are on that match what you see on the geologic map. If you are in Europe, and this is something new, there's something called the right-hand rule. So if you weren't confused about strike and dip, and hopefully you weren't, this is a different way of describing the strike and dip of rocks. It's known as the right-hand rule. And simply put, if there is a rock layer that is tilted, you put your hand on the rock layer so that your fingers are pointing down dip. And what that means is you have to be able to place yourself at the rock layer. If it's exposed, you put your hand on the rock layer and you put your fingers down dip. You point your fingers in the direction that the rock is tilted in, and then your thumb points in the strike direction. And we use azimuth from 0 to 360 with the right-hand rule. So that diagram, the strike direction is 80 degrees. So if you were using an azimuth Brunton, north would be 0, and on your map, this would be the lines that you would draw. So I have that line that would be pointing to about 80 degrees, which is a northeast strike. And then if that's to the northeast, the dip would be to the southeast, and the dip direction would be 170 degrees. So this line is pointing to 170 degrees. And the way that I get 170 degrees is that strike and dip are always 90 degrees apart. This is a 90-degree angle. So if this is 80 degrees, then it's another 90 degrees to the dip direction. So 8 plus 9 is 170. So that would be 170 degrees. Hopefully that makes sense. So I usually use the quad direction. I use northeast or northwest. Some structural geologists like to use the right-hand rule, and they use the 0 to 360. Okay, so here's a little quiz. So here's a geologic map. I think it's kind of the same one I showed you before. So what is the strike given as a quadrant bearing? So question number 1 is look at the strike and dips here. So what would the strike direction be if you were looking at that geologic map? What is the dip direction? And using the right-hand rule, what is the azimuth of the strike? So the right-hand rule, you would have to orient yourself so that your fingers are pointing down dip and your thumb would point in the direction of the strike. Andrew, you still here?
Yes, sir, Professor.
How am I doing time-wise? Am I going too long? I can speed it up.
Yeah, might. I mean, we got some time, but yeah.
Okay. All right.
don't put everyone to sleep, but
No.
I'm
All
loving
right.
this.
Okay, so here are the answers. Here are the answers. So what is the strike direction? I just looking at the geologic map there on top, the strike direction is north 45 degrees west. That's the direction this line is pointing in. So all of these strike lines are north. Instead of north, they're 45 degrees to the west. So the strike direction is north 45 west. The dip direction is to the southwest. And the right-hand rule using the azimuth, you would have to turn around and put your fingers on the down dip and your thumb would be pointing at 135 degrees. So that line right there, it's actually the back bearing would be pointing to 135 degrees. Okay, geologic structures. So let's get into some geologic structures now that we know strike and dip and azimuth and quadrant. And Pennsylvania is the best place in the world to talk about this. Anticlines, synclines, plunging folds, faults. Here is the digital radar map of central Pennsylvania. And just to kind of orient you as to where we are, Harrisburg would be just out of view. This is the Great Valley. Harrisburg would be over here a little bit more to the east. Carlisle is dead. This is South Mountain. So this is where the turnpike comes out of the last tunnel. You can actually see the turnpike there. And that's coming into Carlisle. Altoona is right here. And there's New Paris anticline. So those of you that have been in New Paris, that's where New Paris is. Notice how these rocks zigzag back and forth. The ridges here in Pennsylvania, these huge zigzags, are indicative of what's happened to the rocks in this area. And we see that on a smaller scale here. This is a beach exposed in England. And these rocks have been bent and contorted and worn away by the ocean. And you're seeing anticlines and synclines here that are what we call plunging. So let's get into some structural geology. So we've been talking about structural geology, but let's look at what the forces of the earth can create. So rocks can be deformed by stress. And there are basically three types of stress that act on rocks within the crust of the earth. The first type of stress, well, all of the stress that acts upon rocks within the crust of the earth can result in strain. And strain is what the rocks are left looking like after they are deformed. So every time rocks are bent or broken, that is a type of deformation. There are three basic forces that act on rocks within the earth. The first force is tensional or tension, and tensional forces pull rocks apart. The second type of force is compressional, where rocks are squeezed together. And the third type of force is shear, where rocks are sliding past each other. So you can get one of those acting, you can get several of those acting together, but tensional, compressional, and shear will deform rocks within the crust of the earth. And each one of these forces results in a different type of deformation. So we normally categorize deformation into two groups. There's brittle deformation and ductile deformation. So in structural geology, brittle deformation is exactly what it sounds like. I usually keep a pencil handy so I can snap it. Brittle deformation is this. You have a solid, I have a pencil, you have a solid rock layer, and the rock layer is exposed to stress, and it snaps and it breaks. The pencil is brittle. That's brittle deformation. It tends to happen higher up in the crust of the earth where rocks are not softened by heat. Faults, joints, fractures are brittle deformation. Ductile deformation happens deeper in the crust of the earth, miles down where rocks get hot and soft and they can bend and flow. And that's what forms things like anticlines and synclines and folds and foliation. So the rock on the left down here, this is a sedimentary rock that's been broken by small faults. that's brittle deformation. When you see a rock that looks like this, that's folded and contorted, and the layers are no longer horizontal, that is ductile deformation. So a fault is a fracture in rock layers that is brittle deformation. And any fracture in a rock layer along which movement takes place is a fault. And when you have an earthquake fault, sometimes they're vertical, but most often they are diagonal. And fault language, the break in the rock is called a fault plane. The exposure of the fault on the surface of the earth is called a fault line. If you have a movement of the two different blocks and it forms like a hill or an escarpment, that's called a fault scarp. And then we have the hanging wall and the foot wall. So these are terms that go back to miners. And the picture on the right, when miners encountered a fault below the ground, if they had a tunnel, the hanging wall block is called a hanging wall because it would hang over them in the tunnel. The foot wall would be below the hanging wall. So every fault tends to have a hanging wall and a foot wall. And this may be a myth, but they used to say that the miners would be able to hang their lanterns on the overhanging hanging wall. So the hanging wall hangs over you. The foot wall, the reason we call it a foot wall is because separate the two fault blocks. You could walk up the foot wall. So here's a foot wall. You could walk up the foot wall. It's like the side of a hill, but you can't walk up the hanging wall. You'd be upside down. A skilled mountain climber can climb an inverted hill like that. So hanging wall, all right, foot wall. And those two terms come into play with earthquake faults. So there's basically three types of faults that occur with rocks. The first type of fault is called a normal fault. A normal fault is usually caused by tension, where the rocks are pulled apart. If the crust of the earth is pulled, relative to the foot wall. And you'll see that in the first diagram here. So hanging wall, foot wall. A reverse fault is caused by compression if the crust is squeezed, and that causes the hanging wall to move up relative to the foot wall. And then a strike slip fault is caused by the third type of stress, shear. That's where there's very little vertical motion, but the blocks slide past each other. The San Andreas fault is the classic example of that, and that is called a strike slip fault. Normal faults and reverse faults can form some very, very unusual topography on the surface of the earth. One of the most classic ones is called a Horst and Graben, where you have a series of faults, normal faults that form where the crust is being pulled apart, and you get drop down blocks that form valleys and raised blocks that form mountains or ridges. And there are some very famous areas that have Horst and Graben features. Along a fault surface, on a fault plane, wherever rocks move, we often find slickensides. And there are slickensides in the New Paris Quarry. Some of you may see these little unusual stepped-like blocks of minerals on the surfaces of rocks that you find. This is a really, really good example of slickensides compared to a penny. They're small, but they're really, really well defined. You have a smooth surface, then a little drop-down edge, and then a smooth surface and a drop-down edge. They look like little steps. And when two rocks slide against each other, one fault block will move down, the other one will move up. The upper block will scrape against the lower block and create a series of little stepped mineralized features called slickensides. And when we find slickensides, we can tell the relative motion that the fault moved. just based on slickensides. The upper block, if the upper block moves down, those little steps are in the same direction as the upper block moved. When you find slickensides, the first thing we do is you rub your finger on it, and one direction will feel smooth and the other direction will feel rough. You'll bump those little steps. You move your finger down the slickensides, and the smooth direction is the direction that the upper block moved. So in the direction in this little picture right here of the slickensides, the upper block that was against this piece slid from left to right. And if you rub your finger in that direction, that's where it will feel smooth. Probably one of the best examples of Horst and Graben is in the state of Nevada. This is large-scale Horst and Graben. This is the Basin and Range province. And in Nevada, in this region out west, the crust of the earth has been stretched and huge blocks of rock have dropped down, leaving higher ridges, which are the Horsts. And pretty much here's the outline of the state of Nevada. And all of these ridges are Horsts, and the valleys between them are Grabens. And if you ever go to Las Vegas kind of sits right in the middle of Horst and Graben topography. Anticlines and synclines. All right, so now we get into the folded rocks. Anticlines and synclines. An anticline and a syncline are caused by compressional forces where the crust of the earth is squeezed together. You can get anticlines and synclines in sedimentary, in igneous, and metamorphic rock. Here in Pennsylvania, they're more common in sedimentary rock. We see these all across the central Appalachians. In many places, they control the topography. An anticline is an upward fold in the rocks, and a syncline is a downward fold. Often, anticlines and synclines are paired, and you'll go from anticline to syncline, anticline to syncline, anticline to syncline. The center of the anticline, or the center of the syncline that divides it in half, is called the axial plane. The sides of the anticline and syncline, where the rocks are bending down or bending up, are called the limbs, and they can have different angles, different types of surface expression. Anticline and synclines are two of the most common features here in the Appalachians. Based on the angle at which the rocks are tilted, we classify anticlines as, number one, symmetrical. A symmetrical anticline has an equal dip. The beds on the left or the beds on the right, or the east and west or the north and south, the beds on either side dip at a very, very close angle to each other. And you can see the strike and dip symbols here. The beds are both dipping at 50 degrees. Anticlines have the oldest rocks exposed in the center and the youngest rocks out on the limbs. An asymmetrical anticline is one that has one limb steeper than the other. And those are very common here in the Appalachians. Then you can get an anticline that begins to get pushed over more. And if the limbs appear on top of each other, we call that an overturned anticline. These can be difficult to map in the field, and we use a special symbol with the strike and dips to indicate an overturned anticline. Then the ultimate, which is not up here in one of these block diagrams, but is down here, a recumbent anticline is if the left and right limbs are completely horizontal and the anticline is flopped over on itself. And you get a repetition of the same rock layer back and forth through the cross section or exposed on the surface of the earth. We get the same thing with synclines. We can have a symmetrical syncline where the limbs on the left and the limbs on the right of the axial plane dip at the same degree. We can have an asymmetrical syncline where we have different dips. And we can have an overturned syncline where we use a special symbol on the geologic map to represent that. Then the ultimate is the recumbent syncline, which I've used the same diagram, but that would be the recumbent syncline in there. So we go from a recumbent syncline to a recumbent anticline. And this could be one continuous ridge here in the Appalachians going across several miles. where the anticlines and synclines are joined by mutual limbs, but go from symmetrical to asymmetrical. And here's a pretty nice example. So there's a geological notebook there, a yellow notebook on the right-hand side. So what do you see? So if I asked you this if this was a structural geology quiz for beginning students, I'd ask you to label as much as you could. So what you're seeing here is we have, this is an anticline on the right, and there's a fault that goes through here. So not only is it an anticline, but I want you to notice, trace this rock layer out here, and you'll notice it continues down here. It's been broken and offset. So not only has this been folded, it's also been faulted. This is a reverse fault. This right-hand side has been shoved up, all right? And then we go down into a syncline, and the syncline appears to be asymmetrical. So look how steep. So here's our syncline, and these beds here appear at a shallower dip than the beds over here. So we have an asymmetrical syncline, and we also have pretty much, it looks like a slightly asymmetrical anticline. There's a lot of other things going on in here. There are joints and cleavage planes in here also. Notice how the rocks are fractured going up and down across the layers. And there's multiple faults in there too. So what do you see here? So not quite sure the location of this, but same thing. This is a road cut along a highway. So as a structural geologist, you would have to map this on a map and identify the structure. This is a beautiful example of an asymmetrical anticline. So we have a shallow, this is an anticline. So here, these beds are vertical. It's asymmetrical. It's not overturned yet because this limb is not lying on top of this limb. It's just short of being overturned. So we have a shallow dip here. We have a very steep dip here. The axial plane would run up like this. So the axial plane is tilted at just about the same angle as these beds would look like. They're about 45 degrees. So here's a couple of other examples. We've got some really nice folded rocks in anticline and in overturned syncline on the right-hand side. So we're coming down into a syncline here, and they share a limb. These are sandstone layers. So we have a syncline, and then we go right up into this really sharp kink fold of an anticline. This is definitely asymmetrical. These beds here are vertical. These beds are tilted at about 45 degrees, and things are pretty mashed up in here. And I want you to notice what's happening in here. It's almost, this anticline is plunging. It's tilted and diving down into the earth. So here's a structural geology problem. What's on the left-hand side here? Is that an anticline or is that a syncline? And how do you tell? Is that an overturned anticline or is it an overturned syncline? And that's part of the problem that a structural geologist often has to figure out. Based on just what you see in the photograph there, it can be very difficult to tell. Is that a syncline that's been folded over to the left, or is it an anticline that's been folded over to the right? And here's what would make the difference. Where's the oldest rock layer? If the oldest rock layer is this one, it's an anticline. All right. If the oldest rock layer is this one, it's a syncline, because the oldest rock layers are at the bottom of a syncline. The oldest rock layers are in the core of an anticline. So what you would have to do is, if you analyze the age of the rocks, wherever the oldest rock is, that would determine if it's an anticline or a syncline. This happens to be an anticline. That's an overturned anticline. So here's what we would do to produce the cross-section of anticlines and synclines. That's what the geologic map looks like up on top. And then, so that's the surface expression with strike and dips. And that's what the raised relief map with the ridges of more resistant rock, and the cross section down below looks like. And just another block diagram showing this is very typical of here in the Appalachians. We don't see as dramatic of rocky outcrops like this because of our humid climate. But if we didn't have a humid climate, this is what the mountains would look like in central Pennsylvania. Anticlines and synclines are often connected in a sequence. They can be symmetrical or asymmetrical or overturned. The rock layers will come up to the surface, dive back down, come back up, dive back down. You'll get repeating ridges of the same rocks. Sometimes these are called hogback ridges. We have roads here in western Pennsylvania, central Pennsylvania. Sometimes the roads are called hogback road because they follow these ridges. That is caused by compressional forces. Anticlines and synclines will often plunge. So try to visualize this. If you have rock layers that are folded into an anticline, sooner or later that anticline has to end. Can't go the whole way around the earth and come back again, right? So what anticlines and synclines do is an anticline will be dipping and will dive back down into the ground, and eventually the rock layers flatten out again and become horizontal. And a syncline will do the same thing. A syncline will plunge down into the earth, figure a three-dimensional, like a ship sinking, and then eventually it flattens out and becomes horizontal again. And on a geological map, that is what they look like. So here is a plunging anticline. That's the cross section. There's the anticline. Here's what the surface expression of rock layers look like. And this should be, you saw this in an earlier slide. This is what the geologic map of Pennsylvania looked like with the zigzag mountains. The strike and dip symbols indicate that it's an anticline. And that is the symbol. The rock layers are pointing away from the axial plane, and that is the symbol for an anticline. And the arrow shows the direction it's plunging in. So if this were a geological map, that's an anticline plunging to the north. This is a syncline, and the strike and dip symbols point towards the axial plane, so the limbs are like that. And that is a syncline. The arrows point in. The limbs are dipping towards the central axial plane, and that's a syncline plunging to the north. And then it's connected to another anticline plunging to the north. And same thing, this is very, very typical of here in Pennsylvania. So here's kind of a three-dimensional view of how that happens. This is an anticline that's plunging to the north back into the earth and eventually flattening out. And that's what it looks like. One rock layer, and then there's multiple rock layers. That's the geologic map. There's the cross-sectional view. And here's a plunging syncline. It's coming towards you. So picture like a sinking ship. There's the limbs of the syncline. And on the surface of the earth, you get the same shape as an anticline, but the plunge is open in the direction of plunge for a syncline. And there's the geologic map in the block diagram view, cross-section of that. And that's why Pennsylvania looks like this. So this is that's a plunging anticline, plunging synclines. Touch the screen. These are plunging anticline, syncline, anticline, syncline, anticline, syncline, anticline, syncline. When you go through Blue Mountain and Kittiny Mountain, here's an anticline, that is an anticline, and it's plunging to the southwest. Altoona, Pennsylvania, lies at the beak or the point of a plunging anticline, plunging syncline right here. So, and there's the kind of cartoon block diagram of how that happens. And this is a result of the folding and the erosion of all the softer rock layers. All right, so here's another quiz question. What do you see here? So this is a high altitude photograph of a region. This is in Oklahoma, and you're looking at rock layers. And this is off Google Earth. And obviously there's some rock layers here that are making that zigzag pattern. I can tell you these are folds. The rock layers have been folded and eroded. So do you have an anticline and a syncline, or two anticlines, or in what direction are they plunging in? And I'll show you the solution. There it is. So on the upper right, that's an anticline plunging to the northwest. I didn't put the degrees in there, but I put the symbol, the heavy arrow, shows a plunging anticline to the northwest, and the two smaller arrows show the direction that the rocks are dipping away. You can actually see the bedding surface right here. You can tell this rock is dipping off to the northeast. So there's the strike and dip symbol, indicating that this is an anticline. Then you're going right down into a syncline. So they're sharing a limb here. So that's the strike and dip symbols for a syncline. The syncline is also plunging to the northwest, and those two black arrows go along with the symbol for a plunging syncline. So that's actually one of my quiz questions for students. They have to place those labels on the map. Folds can be quite large. These are the Alps, the Swiss Alps. So if we think the folded mountains here in Pennsylvania are big, if any of you have ever been to the Alps, you can see anticlines and synclines that stretch for 20, 30, 40 miles. And the Alps themselves are a huge system of intensely deformed, ductily soft deformation rocks, when these rocks were miles below the surface of the earth. And now they've been uplifted and eroded. And here we have, there's a nice example right there. That's a recumbent anticline. So you can see that this limb up here is over that limb, and it comes up, and then it's recumbent, it's folded over. And there's all kind of neat structural stuff that's happening in there. So oftentimes we're just almost done. So thanks for sticking with me. So oftentimes when rocks fold, we get a second type of brittle deformation called cleavage. It's not the same as cleavage in minerals. Cleavage in minerals is when a mineral will break on a flat surface because of atomic planes of weakness. Cleavage in rocks is caused by compressional, ductile deformation, or sometimes extensional ductile deformation. You're looking at a slightly asymmetrical anticline. These are layers of sandstone that come up and wrap around. Got the rock hammer there for scale, but notice these cracks that extend. They're a really big one. These cracks that extend through the rock. Here's the labeling. There's the axial plane of the anticline. It's slightly asymmetrical. These are the bedding planes. Those are the different layers of rock that have been folded. And then we have these other cracks that radiate out roughly parallel to the axial plane. And this is called axial plane cleavage. And it is a structural feature that forms within folded rocks if the rocks have the right composition. And we see this quite commonly. We can use axial plane cleavage to identify the difference between anticlines and synclines, even if they're spread out miles. If the limbs are miles across, we can use the orientation of axial plane cleavage, or cleavage planes in the rock, to tell us whether we're dealing with an anticline and or syncline, even if we can't see both of the limbs. So that's another structural feature. Here's what it looks like in a diagram. So here's an anticline, limbs of an anticline, and the dashed lines here, that's the axial plane, which divides the anticline, and that is the axial plane cleavage. The cleavage in anticlines and synclines is caused by compression. It's also caused by slight metamorphism, which causes the minerals in the rocks to align in layers. And it's also caused by something called pressure solution. When you squeeze rocks deep within the earth, some of the minerals in those rocks will begin to dissolve. And that leaves voids where the rocks will come together and form fractures, and that is the cleavage. It's a fairly complex structural feature. This was a field trip that we took down to Hancock, Maryland, along the C&O Canal. This is called Round Top Hill. Can you identify the structure that's back here behind me? What I was trying to explain to everybody. This is a syncline. So that is a syncline. And you can see the layer wrapping around, and that is all of these fine cracks running through there that are really mashing the rock apart. That is axial plane cleavage. So a lot of times rocks are broken by joints. These are real common in the New Paris Quarry. Joints are fractures that are structurally related. This is brittle deformation, and joints are fractures in rocks that are caused by either compressional or tensional stress. The rocks can either be stretched or squeezed, and they will develop vertical cracks in them. And what makes a joint different from a fault is in order to call it a fault, you have to have movement. Joints are just cracks in rocks where the rocks open up, but there's no vertical movement. And oftentimes in igneous, metamorphic, or sedimentary rocks, we'll see these vertical cracks, and those are joints caused by compression or tension. If you just have one set of vertical joints, that's caused by what's happening down here on the right. The rocks are being pulled apart, and that causes the series of roughly parallel vertical cracks. If there's compression, we tend to get intersecting sets of joints where the rocks fracture in intersecting angles. And we can use the pattern of joints in rocks to figure out, are we on a limb of an anticline or the limb of a syncline? Have the rocks been subjected to tension, or have they been subjected to stress? And I always bring our students the joint patterns. This is the New Paris Quarry. This was an earlier slide. The joint patterns on the bedding plane in the New Paris Quarry are these. They are on the western limb of the anticline, and they are tensional joints. What happened as the rocks were folding, the limb of the anticline was stretched, and that caused the rocks to split open. And then also at New Paris, we have intersecting joints that were caused by the squeezing of the rocks together, and those are called conjugate shear joints and strike joints. It can get quite complex to map these all out. So I'm going to leave you with this. In structural geology, this could be a whole nother 3 or 4 hour class. In structural geology, one of the more complex things that we do is we map geological features, anticlines, synclines, strike and dip, faults, joints, axial plane cleavage. We map them on something called a stereo net. A stereo net looks like a globe of the earth with latitude and longitude lines on it, but you're looking down into a bowl. So this is a bowl. It's like looking into the bottom half of a globe of the earth. Picture a globe of the earth that's made of glass and transparent, and you take off the northern hemisphere and you put the bottom half of the globe on the table and you look down into it. And these lines are strike and dip lines. And we orient the bowl north, south, east, and west. And then we do this with, you can do this on the computer, but you can do it with, you can buy StereoNet paper. And we can plot strike and dips on a stereographic StereoNet. And it represents the plane of the rock, the dip, the strike and dip, projected onto a one-dimensional piece of paper, but representing a three-dimensional bowl. It's one of the more sometimes confusing things that we do in structural geology. So what that dotted line, what that's showing is that is a rock layer that is north 22 degrees east. It's striking to the northeast 22 degrees to the east from north, and it's dipping at 20 degrees to the southeast, and that's what it would look like on a StereoNet. If you want to play with this, there is an online website called Visible Geology, and depending on how fast of a computer and connection you have, If you go to Visible Geology, you can play with geological block diagrams. You can play with stereo nets. And when you open up the stereo net, you'll see something that looks like this, and you can click on it and you can move the circle around and it will tell you you can use azimuth or quadrant, and you can project the plane of a dipping rock surface. So what I've done here is that's a strike. I shouldn't have done it. That's a strike using azimuth. You can see the 350. So that's a rock that's striking 350 degrees and it's dipping 27 degrees to the east. So that's what it looks like on a stereo net. So believe it or not, that purple line is projecting the attitude of a rock layer. 350 degrees, that would be north, 10 west, 27 degrees to the east of a dip. And here's just another one. This would be, that's the projection of a rock layer that's striking 70 degrees and dipping 29 degrees to the southeast. So picture, that's what a rock layer looks like when projected onto a flat piece of paper that actually represents a three-dimensional bowl. So whew, and that is the end of my presentation.
Wow, that
Well,
was an education in structural geology. That was a little bit more than an introduction.
it was a
After we
lot.
got
I know I went kind of long, but there's a lot to cover.
no,
Now,
no, that
if
was
you
absolutely amazing. And
if you want to
I,
stick around for a few minutes, I can show you that website and do it. I can do
well,
it live.
let me just say first.
What's
Let
that?
me just say
All
first.
right. Let me
So
see.
for,
I lost my screen here. Let me see where I went. Oh, there we go. Okay. Phew. All right. Well, I tried to pack in, believe me, I did not. I tried to hit the highlights. There's a lot to structural geology, but I did that for you because you wanted a structural geology briefing.
no, so what I was about to say was first there was James Hutton, second there was Charles Lyell, and
But
then
before that,
third, well, hold on,
but
third
first was, yeah.
we have Steve Lindberg,
Oh,
Geology Club presentation, because this is now the defining presentation on, I mean, anyone who wants to know anything about structural geology, they just need to go. Once we get this up on YouTube, this will be the link. I mean, wow. I mean, this is the course right here. So
it's just, we just scratched the surface. So, now, if you want, we could actually do, we could do a structural geology class at New Paris one afternoon.
that might be interesting. Yeah, no,
Because I have at least 25 Bruntons in our geology department, so everybody could use a Brunton, and I could show you how to measure strike, and dip, and trend, and plunge, and azimuth, and
no,
stuff.
I like Ted Snipper's comment right here. Do we get a certificate so we could do the school of
School
Professor
of
Steve
Structural
Lindberg
Geology.
and
I see there's a lot of comments up here in the chat. I didn't get a chance to look at them.
basically how do they know the levels of layers? Core sampling?
Yeah, like
Basically.
yeah, core sampling is very important. Like here, up here on the plateau where Johnstown is, we do have folds. The rock layers, in many places, the rock layers are near horizontal, but the anticlines and synclines up here on the plateau are very gentle. The limbs are 3, 4, 5 miles apart, and the dips are on the order of like 2 to 3 degrees to 5 degrees. There's places where they're dipping more steeply, like if you go up over Laurel Mountain from Johnstown into Ligonier, and then up over Chestnut Mountain down into Blairsville, you can see the dips are much steeper. But the main way that we know what's down there, like 5,000 feet, 10,000 feet, 15,000 feet, is core drilling. And I think that I double check me on this, but the deepest well ever drilled in North America was in Oklahoma, and I think it went down 37,000 feet. So you had 37,000 feet of core.
Yeah, that's a lot of wood boxes with core samples in it.
Right. Someone said that they see a lot of that when they're up in Maine. Yeah, Maine has some pretty complex geology. You got sedimentary, metamorphic, and igneous rocks, and they are really mashed up because Maine was the location of several northern Laurasian continental collisions. You have the Grenville orogeny, the Taconic orogeny, the Acadian orogeny. We were smacked by Baltica. We were smacked by Avalonia, and the focal point, the epicenter of those collisions was up in the New England coast. And there are still pieces of other exotic terrain, still pieces of other continents that are fused to the New England coast. When you drive up through Massachusetts, Rhode Island and Massachusetts, you're driving across rocks from Avalonia. They're not original rocks on the North American continent. They're pieces that were fused to us. So
Very cool. Very cool. Yeah, that was actually my mom up in Maine watching tonight. So Ted Snipper asks, have the geological maps of PA been updated since the 1800s? I believe
yes, yes, and some of the rock formations are the same, like the Conemaugh group, the Allegheny group, the Mauch Chunk, and that's the geological branch known as stratigraphy. Stratigraphy is mapping the specific rock layers and naming them and figuring out how they intertongue with each other. Some of them have been renamed. Some of them have been combined. Some big rock formations have been split apart into smaller ones. In stratigraphy, we call them stratigraphers, we call them lumpers and splitters. Splitters like to break things apart into smaller units. Lumpers like to put things together into bigger formations and groups to make it easier. So it's kind of remarkable that the geologic maps that were made of Pennsylvania in the middle to late 1800s are still pretty accurate today. But it depends on the scale. You know, what scale do you want to map at? If you're making a map that 1 inch is 1 mile or 1 inch is 50 miles, like the little pictures, the photographs that I showed you in this presentation of the anticlines and synclines that the people were standing next to, those won't even show up on a geologic map. We don't even map those. They're too small. They're too small. You can't even see those. If you've ever used a standard topographic map, like a printed 7.5-minute topographic map, 1 inch on a topographic map is 2,000 feet. So what that means is if you have an anticline or syncline that's 100, 200 feet across, you can't even, it's as thin as a pencil line, both limbs and the entire structure. You cannot map an anticline that's 200 or 300 feet across on a 1 to 24,000 scale topographic map. It won't even show up. We don't even map those things. The only way they'll show up on a map is if you need a scale of like 1 inch equals 100 feet, 1 inch equals 200 feet. Nobody really maps on that scale. The New Paris, well, for instance, the New Paris limestone quarry on a 1 to 24,000 scale topographic map, that's the size of, it's smaller than a pencil eraser. You couldn't show any of those rock layers in a circle the size of a pencil eraser. So picture that. The New Paris limestone quarry, for as large as it looks with those big massive rock layers, they wouldn't even show up on a standard geologic map. There'd be a little dot. So
very cool. Very cool. Well, I'm gonna kind of move things along here a little bit. We are at 9:35. This is probably the longest meeting we've ever had. But it is time for the giveaway. So I am going to do this on my phone this time, so everyone's seeing that. We have real quick, if who was it? Kelly McEntee, you have like 5 seconds to put in a new number into the chat because you put 267 and we had said 1 to 100. So I'm going to give you a couple seconds, but other than that, we're just going to go ahead and do this. All right. So the number currently is 2. All right. Looks like. All right. She got 76.
Yep, she got her number in.
Yeah, Kelly, do it again because someone's already picked 76. So one more time, Kelly. All right, 53. All right, I am hitting generate now. The number is 63. So who is closest to 63? We have a 57 with Deb Bright.
57. It looks like that might be it.
Yeah, Deb Bright. All right. So Deb Bright has won tonight's giveaway. I will be contacting you to get your information, and then I will give that to Jeannie so she can also send you the her detective kit. So thank you very much, Deb Bright. I will message you. No worries. Awesome. Yeah, thank you. Cool. All right. Well, this has been another amazing meeting. This will be standard for geology going forward. I'm going to send this out to everybody. Thank you, Steve. Professor, you were amazing as always.
You're welcome. I'll print up a certificate and I'll send it to you and everybody that was here tonight for sitting for that long and listening to all that. They deserve a certificate. So
there we go. That's awesome. That's awesome. Yeah, no, we'll send that out. We'll email that out to everybody. Very cool. All right. Well, Andy, do you have anything?
No, just thanks to Steve. That was an awesome talk. It was a ton of information, but it was presented very well. It wasn't dry or just completely over everybody's head. The way you present it is it makes make it very easy to understand. And I appreciate that.
thank you.
Everybody keep an eye on your emails for events, and we'll see you here next month. We'll see you at Rock Swap. We'll see you at
National Limestone.
National Limestone. Yes, I couldn't think of it. National Limestone in Mount Pleasant Mills.
Yep. All right. Well, thank you all. And don't hesitate. If you all have any questions, email us. We're always happy to answer. And thank you all. We'll see you next month.
Thank you, everyone.
Thanks.
Bye.
Thanks, Ed. Good night.